What's going on, linear algebra bros? In this video, which is the last installment of the composition series, I'm going to discuss the invertibility of matrix transformations. So you may recall with your work with ordinary functions that the operation of composition is a necessary operation to verify that two functions would be inverses of each other. So that implies some functions have functions that kind of cancel out their operations, meaning that functions have an inverse function. But not every function has an inverse that's a function, and since transformations are kind of like the linear algebra version of a function, we want to kind of make ties with what we already know about composition as it relates to the invertibility of a function, and in this case, a matrix transformation. So I have a result here that will allow us to ascertain if a transformation has an inverse transformation. It says here, if capital T, which is meant to designate a transformation, maps n space to n space, is a matrix operator. Okay, so not only is it a transformation, but it's an operator because it's going from one space back to the same space, whose standard matrix A is invertible. So if the standard matrix being used for that transformation is invertible, then that automatically implies that the transformation as a whole is invertible. And this would be the notation representing what would be the inverse transformation. And this actually can be thought of as the original transformation, only using the inverse of the original standard matrix. Okay? So again, weird, wacky thing happening with the instructions, but we're going to do an example. Let T sub A, this is going to be the operator that projects each vector in R2 onto the x-axis, and then T sub B is the operator that rotates each vector in R2 counterclockwise about the origin through an angle of 60 degrees. We want to determine if T sub A composed with T sub B is invertible. Okay, so there are two parts to this solution. Number one, let's think about what the standard matrices we should use are. Okay, T sub A is a projection transformation projecting onto the x-axis. So the standard matrix to use for that, 2 by 2, 1, 0 is going to be the first row, 0, 0 the second. And then the matrix B is a rotation operator that rotates counterclockwise through an angle of 60 degrees. So we'll have to do R sub 60 degrees. So that's cosine 60 degrees, sine 60 degrees in the first column, negative sine 60 degrees, cosine 60 degrees in the second column. And here's how that simplifies. Cosine of 60 is 1/2, sine of 60 is radical 3 over 2. So negative radical 3 over 2, positive 1/2 for column 2. That takes us to the second part of the solution. Bracket T sub A, circle T sub B, really amounts to the product of the standard matrix A times the standard matrix B. So I'm going to bring those two matrices into the mix now. And multiplying these two together, we're going to get 1/2 negative radical 3 over 2 is the entries in row 1, and then 0 and 0 is the entries in row 2. So that's the standard matrix for the composition. we want to determine if the composition transformation is invertible. Well, it boils down to seeing whether or not this 2 by 2 is invertible, and we have a way of determining that with a little formula. It involves some crisscross multiplication. You may recall AD minus BC. Okay, in this case, it's going to be 1/2 times 0 minus negative radical 3 over 2 times 0, which gives us 0. So that implies that the matrix that we have right here is not invertible. It's a singular matrix. So here's what we can say. T sub A circle T sub B inverse does not exist. Okay? So that implies that T sub A circle T sub B is not invertible. And that is our answer to this problem. Now, if you're working with standard matrices that are, say, 3 by 3s, there's not a formula just yet which will help us determine if the inverse of that matrix exists. The best we could do at this point in the course is try to run that matrix through the parallels method, and if we get like a contradictory row, that would tell us that it's not invertible, in which case the composition transformation overall is not invertible. Okay, but if you take a 3 by 3, run it through the parallels method, and you can construct the inverse of that composition matrix, then the transformation is invertible. Okay, so it's either one or the other. All right, kind of like a binary joke. You either like it or you don't. Alright, so that's where the pain and torture, fun and excitement for this video ends. As always, if you have any questions, let me know. Otherwise, thank you for watching.